Hi everyone, this is Madhav. I'm going to be talking to you about really just two kinds of counters. First, we're going to start off with asynchronous counters that are more messy, and then we're going to talk about circuits that can count up synchronously, because that's more predictable, that's what we like. If you're unfamiliar with the words coming out of my mouth, if you know these things, then you will be fine. If you don't know these things, not the video for you. But here's a quick preview of the circuit we're going to build. I'll explain as we go why this thing can build us our asynchronous up counter. We're going to start off by just trying to find patterns when we're counting some numbers up so that we can figure out, okay, how do we put together the right kind of circuit to count up. So I have created this little table where we have these circuits in different cycles. So different cycles meaning different rising edges on the flip-flops. When we have a cycle go by, I increment the count, as you can see, counting up from 0 to 8, or I guess 0 to 7, and then repeating. Can't go to 8 if we only have three binary numbers. Now, one of the patterns I'd like you to note in this table as we count up on the binary number side of things is that if we take a look at the rightmost column, which we might also refer to as the least significant bit, in this particular column, the bit, it keeps on toggling every single clock cycle. Now, what this tells us is that every time we have a rising edge, so let's say it might be one rising edge a second, every second, this bit, this bit, this bit, this bit, this bit, every second we have the bit toggling. Well, this seems fairly simple to implement on a, toggle flip-flop. We just have some toggle flip-flop like so. This is the toggle input, the clock input. I will call this bit this column the least significant bit. I will call it Q0 because it is the least significant. So, 0 makes a good place to start. We have a Q0 naught over here. Okay, so I just want to toggle it every single clock cycle. Well, I'll just feed in my clock signal over here, and I'll just put in a 1 here because I just always want to keep toggling. There you go. So now I have a circuit that changes its Q0 value between 0 and 1 and 0 and 1 and 0 and 1 and so on every single time we get a rising edge. Okay, simple enough. However, we don't just have one bit in the, binary number that we're trying to count up. We have three bits. Let's look at the second bit. Second, because that fits. With the second bit, you'll see that we have two zeros instead of a 0 and a 1. Then we have two ones instead of a 0 and a 1, two zeros, two ones, and the pattern keeps repeating. It looks like instead of, from one cycle to the next, we're not toggling. It looks like we're toggling every two cycles. We're toggling at half the rate that we used to be toggling at. So we could create a second flip-flop for this. It can represent Q1. We have some kind of clock input. We have a toggle. Again, we just want it to always keep on toggling when it's counting up. If it's always toggling, that's going to help us count up. So what I'm going to do is I'll just take this one and feed it through here to say this thing is always toggling as well. Now the only issue is I can't just take, this clock input and then feed it here, because then the circuit, it would be toggling every single cycle, every time there's a rising edge. We don't want to do that. We want to toggle at half that rate. We want to toggle half as frequently as this first flip-flop was toggling. So how can we do that? Hmm. To think about it a little bit, I'm gonna just quickly write out the clock signal over here. So let's say it toggles like so at this rate and so on. Notice what is happening to this particular output of the T flip-flop, Q0 naught. I'm gonna write this here. You'll see why we're focusing on this output in a second. So, at the starting state, I assume that all of the flip-flop values are 0, 0, and 0. So Q naught will start off as a 1. Okay, makes sense. If this is a 0 and that's Q0, then this must be the opposite. It must be 1. Then we have a rising edge. I'm gonna label these rising edges because they're important for us. We have a rising edge, so that must mean that Q0 changes. In particular, it's going to change from a 0 to a 1. And if this is now 1, this must be a 0. So this will go down to a 0. No rising edge. We continue onwards. Now we get a rising edge. Now what happens? Well, we have Q0 is equal to 1. It toggles again. It goes to a 0. If this is 0, the opposite of that must be 1. So Q0 naught, it goes back to a 1. And it carries on like this until the next rising edge, at which point you can look at the table, look at the flip-flop again, and you will correctly be able to analyze that the signal falls down until the next rising edge, at which point it will go up. Note, you have one rising edge, two rising edges in just this period over here. It looks like this signal is half as slow, or half as fast as the clock signal. Let's check that out. Let's count the number of rising edges. So up here we had 1, 2, 3, 4 rising edges. Down here we now have 1, 2 rising edges. So this signal, the output coming out here, it is toggling at half the rate of the clock signal. And this is exactly what we need for the second flip-flop, because we'd like this to toggle at half the rate of, the first flip-flop. We can do that by just having a clock signal. This is like a clock signal that is toggling at half the rate of the earlier clock signal. Now, based on this, you might be able to predict, okay, now we have our third bit over here. It's toggling at half the rate again of this second bit. Why not just repeat the same trick? If we wanted to toggle at half that rate, well, we can predict that whatever the clock input rate will be over here, let's say it is this, then the Q output over here, it will be Q1, and it will be at half the rate of the clock input to this flip-flop. If you don't believe me, try doing the same thing that I did. Try drawing out this diagram. You can keep the Q0 label that was here. Whoops. The Q0 label that was here, and you can try drawing in Q1, see how the changes are. And you'll be able to find something like it should be eh eh it should be like that. and you should have one rising edge instead of two. Pause the video if you want to try that on your own. You should be able to take this information and get this output. However, just with our same assumptions, if you want to just carry on, well, we can just use the same trick as earlier. We want another flip-flop that is always toggling, like so. We want a clock input, not this clock, because that is, it is going way too fast. We want that to be slowed down by half, and we will get our Q2 and Q0. Um, Finally, just note that you can, read out these values. So you can read Q0 and Q1 and Q2 if you read them in reverse, because, this is Q0. It's on the left here, on the right here, so just flip that around. If you read it in reverse, you should get this sequence of 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, and so on, where the sequence changes on the rising edge of the clock. So there you have it. This is our asynchronous counter. Why do we call it asynchronous? It's because not all of these bits, Q0 versus Q1 versus Q2, not all of them will say they won't change at the same time. You'll need a little bit of time for the internal gates inside this flip-flop to do their work. You'll need a little bit of time for the internal gates of that flip-flop to do their work. And while that change is happening, the output here is constant. While this flip-flop is changing, this is constant. So each flip-flop down the line, it has to keep waiting for the last flip-flop to finish its change. It takes a little bit of time. So that's why we call this an asynchronous up counter. It doesn't happen all at the same time. It counts up, but there's a little bit of variance, a little bit of time delays as to when the signals change. Next video, we're going to talk about how to fix that problem, how to make all of these signals change at very nearly the same time.